So before we talk about antennas and what they are and how they are used and how to talk about figures of merit, describing the performance of those antennas, I want to describe a little bit of a scenario that we're going to be walking through. And imagine that we've got a satellite in orbit and it is transmitting a signal to some station on the Earth's surface. So there's a radio involved in this transmitter from the satellite, as well as a radio down here recovering a signal somewhere on the Earth's surface. We know that there is something called the Friss equation, which is defined here. This is one of many forms of the Friss equation. That is something that we can plug values into to characterize the amount of power that any given receiver or transmitter might see. So let me just map some of these terms here. If we think of the satellite itself, the satellite is doing the transmit here. So PT as well as the GT, these are both terms that are connected to the transmitter in this case. So P stands for power. We define power in units of watts, and the transmitted power is basically being fed by some source on the satellite, and it's going to go through some gain figure. So we'll talk about that as we roll this out. The same thing here on the receiver. I've got PR, that stands for receive power, and it's also got receive gain that's associated with it as well. And now, if you look at a couple of other parameters in here, you can see there's a couple of constants here in the denominator. I've got 4 pi. Of course, we know that those are just numbers. We've got this d term, which you might have already guessed is going to represent the distance that separates these. So I'll just draw this little d as a measure, typically in meters or kilometers if we're using SI units. So that's the distance of the satellite to the receiver on Earth. The lambda, we know that there's a constant called c, which is the speed of light, and that is equal to frequency of the electromagnetic wave times the wavelength of the electromagnetic wave. Now I'm going to do a little rearranging here and solve for just PR. And if I do that, all I have to do is multiply both sides of this equation by PT. So on the left-hand side, PT over PT is equal to 1, so I'm left with PR. But now I'll have basically PT times this quantity, and I should just be able to copy this if I do this right, and go ahead and bring it over here. So now just a rearranged form, and now this is exactly the same thing. It's just that instead of solving a ratio of power received by P over T, power transmitted, I'm just solving for the absolute power. It's also common in radio frequency applications to define things in a different scale. Right now, this equation is written out in what we would call a linear form, but we could also define things in a logarithmic form. So using SI units, we can think of PR, and I'll just put in parentheses what the units are. With SI units, power received in the linear form would be watts. So linear is going to basically be units of watts. So that's a common notation to see it with a parenthesis indicating what the units are going to be. In the logarithmic, or more specifically, we call it the dB form, decibels. So if we convert this to logarithmic, imagine if I take 10 log of both sides of this equation, 10 log of PR in watts is the definition of the decibel scale. So it would be dB watts. On the right hand side, let's just follow that through, where if I said well, let me just draw it out explicitly here. If I say 10 log of PR, let's put that in brackets, and I'll say with watts units, then let's just define that as, let's say, PR in dBm units, or I should say dB watts to be specific. And I'll try to give some supplemental material just with a lookup table on how to do those conversions. But all I'm saying is by definition, 10 log of power received in watts is going to be power in dB watts. Now on the right hand side, imagine if I apply 10 log, getting a little tight with my notation. If I say 10 log of PT times GT times GR times lambda over 4 pi d, this whole thing squared, I can follow my logarithmic rules, which you can look up on the internet pretty quickly, or the back of a math textbook, and find these rules. So there's a logarithmic product rule. I'm about to follow the product rule for this, where basically taking the log of two entities multiplied by each other means that we add them. If it's the quotient rule, dividing means we subtract them. And then there's the power rule, where we can take an exponent down and multiply it by the quantity. So let's go ahead and continue to do that. So if I say, if I use a product rule, I'm going to consider my products. There's multiple ways of doing this, but I'm going to go ahead and consider this, let's say, to be product 1, or I should say the first entity, the second, the third, and then let's go ahead and call this the fourth. So I'm basically doing 10 log of 1, 2, 3, 4 things multiplied by each other if I define it this way. You can see how there could be a quotient in here as well, and I could define it differently, and sometimes people do that. But for now, I'm just going to follow the product rule, which means I'm going to reduce this down to basically 10 log of PT plus 10 log of, clear up my penmanship here, 10 log of GT plus 10 log of GR plus 10 log of my final, I'm just going to go and use brackets here, of lambda over pi over 4, sorry, I seem to have lost my 4. There we go. So now that's, apologize for that, and 4 pi d, and that's squared. So let's make a little room. And now if I continue on, so that was equal to this. So now what I can say is PR in dB watts is equal to, we know this, following the same definition of this, is going to be PT in dB watts plus 10 log of GT. So the gains are typically referred to in reference to an isotropic radiator, and we'll have a little bit of supplemental content on that, but we're just going to go ahead and use that definition. So I'm going to say gain in log scale, and we're just going to say dBi, and that's just an indicator to you that it is a reference to an isotropic radiator. And that allows us to be able to add dB watts as well as dBi. You can think of this as a unitless number in that sense. So GT, the same thing goes with GR, is also going to be in dBi. And again, when we talk about the antenna section, I'll try to make that connection. We're going to go ahead and leave this in its form, but what I am going to do is apply the exponent rule here. So if you remember back to the table reference I did earlier, we can take that 2 down and multiply it by the 10. So now instead of saying 10 log of something squared, I can say 2 times 10 log, which would be 20 log. So I've got 20 log, and I've got just lambda over 4, and now I've got my 4 back, 4 pi d, and it's no longer squared, because in this form we've brought this down. So this will be a term that we just calculate out. And again, everything is in the appropriate scale, whether it's dB watts or dBi. We can interchange those components, and now this is going to be in the appropriate form, so that we'll just be able to add that number to it. And the reason I went through all of this is because this is a very common way for engineers to do, especially communication scenarios, to be able to do something called a link budget. And because of the large scale of values, from very small receive values that, as you're about to see when we continue this whole exercise, to very large transmit values. So the dynamic scale of, maybe tens of thousands of watts, possibly going down to, maybe microwatts or nanowatts, or possibly even smaller. This is a big reason why this decibel scale is something that is very commonly used. So with that, we're gonna switch the discussion to these components here, GT and GR, and we're going to spend a little bit of time as we go through the antenna modules and describe exactly what these elements are in this FRIS link budget equation, and we'll put some context on that regarding the satellite communication scenario.